So what is B? B is this vector. And S, what is S? S is the vector pointing to the quasar, this vector. So in fact, I can write it like this. This vector is ST, and this one is B. So I will write B, and both are vectors. That's the basic principle of VLBI for determining what can we do, what are we looking for then. So we have one station, one B, and it has three unknowns here. And then this one is known from the coordinates of the celestial object. Then we can determine. We have three unknowns here, at least three stations. Well, that's not just simple actually, because this tau, the signal, theoretically it was simple, and it is okay. B, vector B is multiplied by vector ST, but the signal needs some correction. There are some systematic effects. One is aberration, diurnal aberration. Let me write it AB. Aberration, because aberration is related to the rotation of the Earth, because these points that the stations are there, they are moving at the same time that the signal comes. This is called aberration because of the rotation of the Earth. Plus another correction, which is related to instrument correction, plus another correction which is related to atmosphere. And it is known that atmosphere correction related to troposphere and ionosphere. Instrument errors are related to the shift and drift of this clock, for example. But normally there is a mathematical model. This is the same, not the same, similar to with GPS, that this can be modeled by a simple relay, real simple model like this. This one is shift, and this one is drift. And the aberration, I write it with another color. Here, aberration is actually 1/c. This is a formula. R dot 2 over multiplied by S, and later I will explain what they are. Tau T. So this is the general formula of the VLBI. And in VLBI, this part, the first term actually, is the pure geometric without any correction, any systematic effect. But the rest are added as the corrections, or systematic corrections that should be considered. Well, but it is very general. Let's consider that we are at the surface of the sphere. And I have a point 1 here and point 2 here, and one meridian goes through this, one meridian goes through that. If it is centered, this will be vector of position, is position vector of the second. And this one is the baseline. So then if I just consider that, then I have lambda 1, lambda 2, lambda 2, and lambda. These are the things that we all know. And the signals comes from the quasars from this direction. And this is pole. So if we write this equation, the baseline, if we multiply the baseline by this coordinate, I can simply, if I write this unit vector in the hour angle coordinate system, which is in astronomy, I can write that this baseline vector multiplied by st vector is bx, by, bz. This should be x, bz. This is inner product. And the unit vector pointing to this celestial ray cosine delta S. Delta S is declination. Declination cosinus HS. Then cosinus delta S sinus HS and sinus delta S. If I multiply these two, I come to this equation, Bx cosine delta S cosinus HS plus By cosinus delta S sinus HS plus Bz sinus delta S. So that's the equation for the baseline. This first term in the equation of the formal equation of the equation. So H actually here, H is called in astronomy hour angle, which is Greenwich sidereal time minus the right ascension of the celestial object, which is S. And delta is the declination, which is this angle, similar to latitude, but in this hour angle system, which is declination. And if somewhere is right ascension, is gamma, which is vernal equinox, then it will be position. So that's the way how to connect this baseline station with the celestial object coordinate. So you have this object coordinate from the space, and the baseline is here. This is the general equation for the EVLBI, but when time delay is measured, and the time delay is measured. But in the case that the frequency is measured, we have another equation. In the case that we use fringe frequency for that, we write frequency is 1 over 2 pi. That's the derivative. Changes of the phase. This is from the physics derivative. This is the phase. It means the phase is a function of time. So already know that phase is 2 pi reference frequency multiplied with this. This is the relation between the phase and the time and delay time. And if I insert this back inside this equation, the fringe frequency will be V0, is reference frequency, T. Based on this principle, we can rewrite the equation of the VLBI observations, this time based on the fringe frequency. So if I consider this frequency, this VLBI observation will change to this V0 over C, and vector B is multiplied by the rate of changes, those which are function of time, then we put the time derivative above them. Like this, it says point is time derivative. Plus, this time, the effect of aberration on frequency, plus the effect of instrument, again on frequency, plus the effect of atmosphere. So if I simplify this term here, it will be very similar to what I have already written, but there's a point that I want to highlight here is, so if you remember, it was Bx, and it was cosine delta, if you remember, cosine delta. But H, if you remember that in the formula, H was GST minus alpha. GST is time. So when I take the derivative with respect to time, it means that I'm taking derivative with respect to H. So on that time was sine, cosine, then it will be sine H. Minus By cosine delta S. This time cosine H. And the last term has nothing. Has nothing because it was not function of H, it was function of C. So this term is multiplied by W because the derivative of H with respect to time will be the rest rotation. So as you see here, when you use phase data, you cannot determine BZ because we don't have BZ in the equation. But when we use time delay or tau, the BZ appears in this term. But when we use for the frequency or the phase, then it is not there. So that's the main important difference, that you know when which quantity you use and what you get from each.